So it's multiple choice questions. 4 possible options are provided as answers to the following questions. We must choose the answer and write only the letter. Now, this is very crucial. And I know I really haven't seen it in grade 12, and I hope you're not doing it, but the examiner only wants alphabet A to D. If you write the actual word or the actual answer, they cannot give you a mark. Another thing, you cannot write A or D or A/D. You cannot make the examiner choose the answer. I feel like if there was one or more possible answer, then they would state that, but most of the time with multiple choice, there is only one. Now remember, if you write A or D, even though A is right and D is wrong, the examiner cannot give you a mark, right? Because you could have written all the options and made them choose. So remember, that is not correct. So we must write down only the letter, which is A to D, next to the question. Remember to always stick to the correct numbering sequence. You write this in your answer book, and they've already given you an example. So let's read the first example that we have. We are told that Vuyo, the driver of a minibus that is moving at a constant velocity. Now remember, when we have constant velocity, there is no acceleration. So what I would do is, as you can see as I'm reading, I'm underlining some of the terminologies, and I tell myself, what do I know about this terminology? Because somewhere, somehow, it is actually going to influence my final answer. So already, if it's moving at a constant velocity, we know if velocity is constant, then acceleration is 0. It's moving on the horizontal road. This guy sees that the sliding door of the minibus is open. He suddenly applies his brake, and then the door closes. So what happens is, he's driving, oh my word, my door's open, and then he puts on his brakes. And then obviously we know, according to physics, you will move forward, and then you move back, inertia, and then the sliding door actually closes. Now we're already learning about the laws of physics. Now, which one of the following physics laws or principles best explains why Vuyo could close the door? The first one is the law of conservation of mechanical energy. Now remember, mechanical energy, or the total mechanical energy in a system, remains constant. Now mechanical energy is the product of EK plus EP. EK is a half mv squared, EP is mgh. So all of this, as long as all the forces remain, are conservative forces that are actually acting on the system. Then we have the principle of the conservation of linear momentum. Now remember, the product of the definition for momentum is the product of the object's mass and velocity. However, momentum states that the momentum of an isolated system remains constant, and momentum is neither created or destroyed, rather transferred from one form to another. So there we have momentum. Remember, linear momentum, not change in momentum. And then we have Newton's first law of motion. And then we have Newton's second law of motion. Newton's first law does not have a formula, but Newton's second law of motion does. The formula that we use is F is equal to ma. F meaning force, mass is your, m is your mass, a is your acceleration. You can also say A is equal to F over m. Now I want to explain Newton's first laws. So Newton's first law, I want you guys to think about a pencil on a dashboard. Let's use the minibus. If you have a pencil on the dashboard and all of a sudden you apply your brakes, the pencil will then suddenly move. What Newton's first law says is that an object will remain at rest or continue to move unless acted upon by an external or resultant net force. When Newton's second law says, if a force is applied on an object, for example, if I was to decide to push Mbali in the one direction, if I apply a force, Mbali is going to move in the direction that the force is applied, which means that the acceleration is directly proportional to the force, but inversely proportional to the mass of that object. Now you can already see, law of mechanical energy, potential energy, kinetic energy, nah, not really going to make the sliding door close. The second one, principle of linear momentum, the product of the object's mass and velocity. And then we have Newton's first law, moving. Newton's second law, applying a force, acceleration, mass, no. Which means Newton's first law is going to be our answer, because this means as the car was driving, the door was remaining at rest. He applies the brakes, that is the external or net force. And then what does it do? It moves forward, which actually closes the sliding door. So that is Newton's first law. So number 1.1 will then be C. Let's move over to the next one. So here we are told we have a 2 kilogram mass piece, which is placed on a 2 kilogram trolley. I just want to underline this. We've got 2 kilograms, which is a mass, and another 2 kilograms, which is a trolley. Now, I want you guys to think of it like this. If I, moi, weigh 40 kilograms and then Bali weighs 60 kilograms, collectively we will weigh 100 kilograms. This question was not really tricky, but you had to remember that if something is on top of something, they have one mass. You don't only take the piece on top having its own mass, but you take the two objects collectively as moving as one. This means if I was to put Mbali on my back and I go into a scale, the scale is not going to say Tobile weighs 40 and then Mbali weighs 60. The scale is going to say 100 collectively. So you must already put that in mind. Together, they make one mass. So we have a 2 kilogram mass, which is placed on a 2 kilogram trolley, and which is at rest. Remember, if something is at rest, then we know that the velocity is 0. It's on a frictionless horizontal surface, so there's no friction. When a force of F is applied on the trolley, remember when you apply a force according to Newton's second law, the object will move in the direction that the force is applied. It accelerates with an acceleration of A. Remember, I can already see we are using F is equal to ma according to Newton's second law, F being directly proportional to the product of the object's mass and acceleration. And this is shown in figure number 1. And then what happens is we have a 1 kilogram mass piece which is then placed on the trolley with the 2 kilogram mass piece and the same force. This is very crucial. The same force is applied on the trolley. Let's look at this picture. We still have the 2 kilogram trolley. Next to the 2 kilogram mass piece, they've added one more. So this means now we've got Mbali, now we've got me, and then we've got Sane. Now there's 3 people. Remember, now together collectively, the 3 are making one mass. Again, you do not look at them individually. So it is applied on the trolley now as figure number 2. Now they're asking us, what will the acceleration of the trolley be at figure number 2? Remember again, they apply the same force. For force, we use F is equal to ma, force being the product of the object's mass and velocity. I actually want to add a slide here. So what you're going to do here, let me just name this as 1.2. I'm going to name this figure number 1. I'm going to name this figure number 2. Remember, with figure number 1, we had 4 kilograms. With figure number 2, remember we had a 2-piece, 1 piece, and the trolley being 2, which gives us 2 kilograms. Now, with figure number 1, we were told that a force is applied. Collectively, they made 4 ma, that was the mass, which was 4 ma. And now we are told, I just want to add this. Now, if you had to look at the acceleration of this, you would say that A is equal to F over 4m, right? That would then be your acceleration. But the important thing that a force was applied on the mass being 4 and then the acceleration. Now, on the 2 kilogram block, again, I'm going to use F is equal to 5. Now, the mass is 5 ma, right? What was I told? If I go back to this question, I underlined it. Let me just go down here quickly. They said the same force is applied. So which means you're not applying the same force. So what this question is actually saying, if I was to pick up Bali and I try to pick up a baby with the same force, obviously the baby is going to be a little bit more light because I'm using the same force that I used to pick up Bali. So the same thing is happening here, which means that the force you've actually applied does not change. Now I want you to see what you're going to do here. Now this is just mathematics. This is 5a. But I'm told that the same force. So if this F is equal to 4 ma, I use the same force to push the 5 kilogram block. What happens then? I'm going to have 4a, 4 ma, 4m. I'm going to remove the acceleration because that is the force that was actually pushing this block to accelerate in this direction. The same force was used to push the 5 ma. What does the question say? They want us to calculate the acceleration that the 5 kilogram block will then move. I'm looking for A on this side. To get A alone, I divide both sides by 5m. 5m, the 5 and the 5 will cancel, m and m will cancel, which leaves my A and this side as well as 4 over 5. The tricky thing was that the same force that was used on this side, if F is equal to 4 ma, the same force, so you just had to substitute it there, and then you equate it to one another to calculate the acceleration. So acceleration will then be 4 over 5. So let's see if we have an option like that here. So moving right over here, there we are. Option number C tells us that it is then 4/5. Now I want you to think about it. You could not have guessed this one. Number one, the one only had 4 kilograms, the one had 5 kilograms. So you don't really know the ratio in which you have used it. Maybe there is a simpler way you could have done it, but I always say using two formulas and actually doing what the question says makes it much more simpler. Don't guess such questions, you have to work it out. The clue was given that it is a force applied and it moves at a certain acceleration. Already in our minds we know Newton's second law. The same force that is applied will move the same block, which is now 5, which has a mass of 5 kilograms. We want to then calculate that acceleration. That is the one way you could have done it. So let's look at another question. Let's look at 1.3. We are told that two cars are involved in an elastic head-on collision. I actually want to explain elastic. Now, when we do the topic of momentum, we can calculate the total kinetic energy before and the total kinetic energy after. It's one of two things. It's either the collisions can be elastic or they can be inelastic. When is the kinetic energy conserved and when is the kinetic energy not conserved? Well, one way to actually remember it, or how I remember it, if you take a piece of paper and you try to stretch the piece of paper, it's never going to come back to being a piece of paper. It's inelastic. It's not an elastic band. If you take an elastic band and you stretch the elastic band and you leave it and then it bounces back, boing, 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 it comes back to its natural form of being an elastic. That is an elastic collision, where before equals after. If before does not equal after, it's inelastic. If before equals after, then it is an elastic collision. So we must really put that in our minds. So we have two cars involved in an inelastic head-on collision. Remember, the term head-on means that one car was coming from the left and one car was coming from the right. Now they ask us, which one of the following combinations describes the kinetic energy? I just want to use a different color. When we talk about the kinetic energy, and remember that EK is equal to a half mv squared, kinetic energy and the momentum of the system. When we talk about momentum, we talk about P is equal to mv. So which combinations will actually work the best? Now I want us to look at kinetic. I just want to rub this off so that I have more space. Now let's see what this question actually says. Remember, with elastic, it's not conserved because of the frictional interferences. Now let's look with the total kinetic energy. Now we know that elastic means not conserved. So it means that number B and number C must be out, because conserved means that it is an elastic collision, which means that before will equal after. So already I'm going to rule out B and C, because if it's conserved, it means it's elastic. They are telling us it's inelastic. I'm only going to cut out number B and C. So I'm only going to work with number A and number D. So now let's see what the other one says. Now we know that momentum in an inelastic collision is then conserved, because the total momentum of the object equals the total momentum of the object after. So I can see this one is conserved, this one is not conserved. So my answer must then be A. Let's go back to it. Conserved is right in this part. However, the total momentum of an inelastic collision means that momentum is conserved. Because remember, if you have an object, P is equal to mv, the object's momentum before will equal the object's momentum after. However, the kinetic energy in an inelastic collision is not conserved. So this one is then ruled out. The only correct one that we have is the number 1.3. Let's look at number 1.4. So here we've got the graph that shows the relationship. So one thing I always tell my kids, if you are given a graph and you're asked about the relationship of something, it's one of two things. It's either you study the graphs and you know how they work and so forth, or my biggest thing, go to your formula sheet. Find a formula that actually works with whatever is given. For example, if you're given a velocity time graph, acceleration time graph, in this case, we're given a power versus a velocity time graph. So you have to look for a formula that uses the two units that you're talking about, and then you can see the relationship between the two. Another thing that you guys need to get used to is that when you have a graph, the area of the graph can tell you something specific about that graph. For example, if you look at a velocity time graph, the area of that can give you the distance, whereas the gradient of that graph can then give you the acceleration. Another crucial thing that you need to remember when you're looking at graphs, you need to look at the shape of the graph, as well as is it a positive slope, is it a negative slope, is it an increasing or a decreasing gradient, right? So let's see what we have here. Let me just take this off here. So we have the graph below that shows the relationship between the power delivered. Remember, power is the rate at which work is done, and power is represented by capital P, is delivered by the engine of the car and the average speed of the car. So here we've got power here, and then we've got my speed or my velocity going down. Now the question here asks us, the gradient of the above graph, what does it then represent? So I'm going to do it the long way around. So let's first see the first one. So first I'm told that the gradient of the graph represents the momentum of the car. Now remember, when we talk about momentum, momentum is the product of the object's mass and velocity, right? Not power. So do not get confused. Power is a capital P. Momentum is a small p. These are the SI units that we actually use to represent these units. So don't get confused. So it's definitely not momentum. Then we have the work done by the engine of the car. Remember, work done is equal to the object's change in kinetic energy. Work done is represented by a W, is equal to the object's change in EK. I'm going to expand this a little further to say that work is equal to, I'm going to expand the EK, which is going to be a half mvf squared minus a half mvi squared. So not really power and time, as you can still see. And then we have the kinetic energy of the car. So what they're telling us is that if you have power on the car and you have a velocity, then the gradient will give you the object's kinetic energy. Remember, kinetic energy is EK. To actually calculate EK, we have a half mv squared, right? Not really with power. And then again, we have the applied force of the engine of a car. This one could actually be correct. Why do I say that? Remember, we have a formula that says P is equal to FV, which means that power is equal to force and times velocity. Making power, if I make force the subject of the formula, let me just write it here. P for power is equal to force times velocity. You find this on your formula sheet or as a representation of power. If I make F the subject of the formula, I'm going to have F is equal to P over V, which then means that the force is directly proportional to the power and inversely proportional to the velocity. What does this mean? Directly and inversely proportional. When the force increases, the power will increase. When the force decreases, my velocity will decrease, and vice versa. So which means that the gradient of a power versus speed or velocity graph will then give you the force. What is the force? It is the applied force in the engine of the car. Remember, if we say power is the rate at which work is done, you need some type of force to actually have that power, right? So that is why we then use P is equal to FW. So the correct answer for this question will then be D. Why do I say that? If you're looking at all the other options, we just have momentum. I think here the examiners thought they could actually trick you with having a capital P for power and a small p for momentum. Now remember, you can use momentum in a car and stuff like that when you are talking about impulse, but not about power. The work done by the engine of the car, we don't really have so much information. We don't even know if there's any conservative forces. With the kinetic energy of the car, they've already given us the velocity with this one, and kinetic energy is a form of just energy. Then the applied force, power is the rate at which work is done, and you need a certain force to help you finish that task. So number 1.4 will then be D. Let's go to the next question. Let me just see if, 1.4. Let's go to 1.5. So now here I'm given a few types of graphs. I just want to elaborate further on graphs, my darlings. Now, in physical sciences, there are a few graphs that we use, but most of the time we use graphs in vertical projectile motion. Now, when we use graphs in vertical projectile motion, we either have a displacement versus time graph, and it has its own distinct shape. It'll have a little curve to it, right? We have a velocity time graph, which is a straight line graph. Most of the time, you have to use a ruler. And then we have an acceleration versus time graph, which is most of the time just one straight line, either being in the positive gradient or positive quadrant or in the negative quadrant. If ever you get a question that is asking you what is happening here or what graph best represents the situation at hand, you must first think about the shape of the graph, especially if it's vertical projectile motion. Think of those three and think about the shape. Rule out any other graph that does not make sense to the situation at hand. So this is what we're going to do. So we have a ball that is dropped from a certain height. Now, which one of the positions versus time graph below represents the motion? Now, I just want to talk a little bit when something is dropped. I first want to talk the long way around. If I have this pen and I decide to throw this pen in the air, everything that goes up must come down. As this pen keeps going up, it reaches its maximum height, and then what happens is at maximum height, the velocity is 0, and then it comes back to the ground. This is what happens. As you throw it up with an initial velocity. The velocity keeps getting less. Let's start at 10. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Then it comes back down. 1, 2, 3, 4, 5, coming down. What does this mean? If you throw an object up, the velocity actually keeps decreasing, going up, and then it comes down. If you throw an object down, the velocity just keeps increasing, moving down, which means we have to find a positive gradient or a negative gradient. But now we must remember, this is a position versus time graph. So let's see, it is dropped. I've already explained what it means when something is dropped and which one of the position versus time graph best represents the motion at hand. So let's start with the first one. So we have number A. I can see that I've got X, which shows my position in meters, and I've got my time. It was dropped. It does start at 0, and then it moves. It has a little curve. Now remember, if something was dropped, the velocity continues increasing, which means acceleration. It means acceleration speeds up. Look at this one. It's also a velocity time graph. It also starts at 0, but it now moves in that direction. This means acceleration is slowing down. Look at the curve of this graph. This one, acceleration. This is some theory that your teacher would have done with you before you actually do the graphs. Now remember, you have to sit down with your textbook and you have to read. Such concepts and theories you will only get if you actually read. So let's look at this one. Then I've got number C. I can see that this is a positive slope, right? Velocity is constant, velocity is positive. Most of the time when we use a straight line graph, it is a velocity. This is a velocity versus time graph, right? This could either be an object that was thrown up or from the ground moving all the way up. Look at number D. Now, number D could have been the velocity of something that was actually thrown down from an initial velocity moving down. This we have a negative slope, right? And it's moving down. I'm going to rule out number C and number D. Why? Because the shapes of these two graphs more or less represent velocity time graphs. Why do I say this? Because the shape of a graph, a position or displacement versus time graph has to have a curve. I'm going to rule out number C and D. Now it's between these two. They did say that it was dropped. If something is dropped from a certain height, we know that velocity keeps increasing, moving down. If something was thrown up, velocity will keep decreasing, moving up. What does this mean? Acceleration is speeding up in the positive direction. So 1.5 will then be A. This means the curve of this graph shows that acceleration is speeding up, that it was dropped, whereas B shows that it was slowing down because it was then actually thrown up. So 1.5 will then be A. So let's see what we have at 1.6. So or something is the main principle. Now we know when we apply a principle, it's something that does not change. Something is the main principle applied when measuring the rate of blood or the heartbeat of a fetus in the womb. Now, before I start looking at whatever options we have, now I want you to start thinking. If a lady is pregnant and she goes and sees a doctor, now I'm not really into medicine, so hopefully I say these terms right, and then they use that scan to actually feel the heartbeat. So the doctor's listening, the doctor will hear doop, 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 right? That is some frequency, some of the waves that the baby's making. Not that the baby's actually beatboxing, but that's the waves or the heartbeat of the child, and that's what the doctor can actually hear. Right? Now we must already think frequency, waves, sound, and all that stuff. So let's see what options do we actually have. Here, the first option, we have the photoelectric effect. Now let's go back. The photoelectric effect is when packets of light, I can actually write it as E is equal to HFO. Packets of light are actually shown into a metal surface. Remember, you usually have a metal surface and they are ejected from that metal surface. And it does have frequency, but it actually talks about the work function and frequency of certain metals and having electrons actually have kinetic energy. Then we have what we call the Doppler effect, when ultrasound beam is passing through a vessel. So here we're going to have FL is equal to V plus minus V of L over V plus minus Vs times F of S, right? So this is the Doppler effect. Now you can see we've got a frequency of the listener, we've got the frequency of the sound source. The listener could be the doctor. What is the doctor actually hearing? Sound source could be the baby. What is the heartbeat of the baby, right? And then we have another one called Huygens principle. Now, what Huygens talks about, I just want to write it over here. It's a statement that all points on a wavefront of light in a vacuum or transparent medium may be regarded as a new wave source. So he talks about diffraction and all that stuff, right? Most of this is what we did in grade 10. He talks about constructive and destructive interference. So not really that. He's not wrong when they talk about frequency, right? But not that. Then we've got another one called diffraction. Now remember, diffraction is the bending of light. Diffraction is the bending of light. Remember, when we talk diffraction is the bending of light around an obstacle. And bending of light can actually be explained using Huygens principle. So now looking at these ones, photoelectric effect does have frequency, but it does not talk about a listener and a sound source. The Doppler effect, yes, does talk about listener and a sound source. Huygens principle talks about frequency in terms of diffraction and constructive interference, and then diffraction is just the bending of light around an obstacle. So 1.6 will then be number B, which is then the Doppler effect. So now we are doing question 1.7. So let's continue with that one. So with question 1.7, we are told that the electrostatic force between 2-point charges, I want to elaborate on the electrostatic force, right? Remember, you can actually use or understand the electrostatic force using the Newton's law of gravity, that the force of attraction or repulsion, which can actually ever happen, is the product of the two masses and inversely proportional to the distance between their centers. So what happens is we've got two spheres. They can either attract one another or repel one another. But one thing that you must always remember, if you make the distance further and further and further apart, if you increase the distance, you reduce the force. If you decrease the distance, you increase the force. So it's just mathematics that you need to understand, which means that the one is directly proportional to the other one, but inversely proportional to the other one. Right. So with the electrostatic force between the 2-point charges that are placed at a distance r apart in a vacuum of F. So here's the two forces, y and x. I can see that both charges are then positive. Now they continue to say that the distance between their charges is changed, and where they don't tell us what the distance is, but the electrostatic force between them becomes 16F. What is the new distance between the new charges? You cannot guess it, you have to calculate it. Let's look at 1.7. Remember, we've got this one, which is y, and we've got another one here, which is then x. The electrostatic force is F is equal to K, Q1, Q2 over the distance between their centers. Now I am told that something kind of happens here, but we know that the force becomes 16, right? We need to find out what is the new distance between them. Now remember that force is directly proportional to the two masses, meaning if the force is 16V, then the masses will then also be, or the product of the two masses will also be, it's directly proportional. However, force and the distance are inversely proportional, which means that if my force is 16 here, the inverse of that, let me just do it the long way around, I'm going to have K, Q1, Q2 all over. The inverse of that, I'm going to have this as 1 over 16, right? Now remember, if it was 1 over 16, you're looking for force, you do the inverse of this, which then gives you 16. The only tricky thing most people would have forgotten here is that the distance is already 16. But the question here, the radius is squared. So now you go back to grade 9. What times what will give me 16? Now I know that 1 over 4 times 1 over 4 will give me 16. Numerator times numerator gives me 1. Denominator times denominator gives me 16. This means I'm going to have K, Q1, Q2 all over 1 over 4 squared. So what is my new distance? So the new distance that I then have is then 1 over 4. Remember, they already given you the distance in full, but remember you had to do the inverse of the force to actually get the distance. Let's see if we have a 1 over 4 there. This is 1 over 7. So for question 1.7, then my answer is D. It is 1 over 4. I just want to go back to this question. You can't say it is 16 because that means the distance is already squared. Remember, the formula says square, so you can't square it. You're looking for the radius only by itself, right? So that is then why we had to do or work backwards. So that is 1.7. Let's see what 1.8 does. This is one of my favorite topics. I love electricity. So number 8, 1.8 says we have 3 identical resistors. So when in physics, if things are identical, it means it is the same. This means if we have got 3 of the same resistance, it means that the resistance of them will be the same, right? Meaning they will all allow the same amount of current through them, except how they are then connected. So we've got 3 identical resistors that are connected to a battery as shown in the circuit below. Remember, the connection of an electric circuit is actually very crucial. Well, with an electric circuit, there's not so much to remember, but you have to remember how it's connected. So let's just look at this one here quickly. So I can already see here that I've got 2 resistors in parallel. How do I know these 2 are in parallel? When my current gets here, I've got current that splits up there, and I've got current that splits there. The current goes around, comes back, and then the same current will then pass through the R. So this R and this R are resistors in parallel. Now we know that resistors in parallel are current dividers, and the potential difference will be the same. Resistors in series, the current will be the same, but then they are then potential different dividers. Something to also remember, that the reading in voltmeter 2 will be the same for this one and then for this one. So already I've looked through all my possibilities. Now it continues to say, which one of the following best represents the relationship between the readings in the voltmeter? So what this means, we want to know the answer of voltmeter 1, whatever it might be, what would it be to the voltmeter 2? Will it be half of that, 2, equal, or a third of that? Remember, you cannot guess it, we have to work it out. So let's look at 1.8. I'm going to do it the long way around. Now, I like using hypothetical assumptions when they say things are identical. I always think that the best assumption to use is 1. So let's say this was a 1 ohm resistor and this was also a 1 ohm resistor, right? And this was also a 1 ohm resistor. They did say that the resistors are the same. So 1, 1, 1, 1, 1. The famous formula is R is equal to V over I. So the famous formula that we use for electric circuits is R is equal to V over I. You can calculate anything with these two. So starting off here, if I'm going to calculate the total resistance here, now I know that the same current will pass through here. So I'm going to say that hypothetically speaking, if my current is 1 ampere, now I know for the total resistance here, I can then use the same current because the same current is going to move through there. Let's start with this one over here. if I say R is equal to V over I, and I say V is equal to Ri, because they asked me about the potential difference. Now, if you say 1 over 1, so now remember, if you're looking for resistors in parallel, let me work this out here. Remember, you say 1 over R parallel is equal to 1 over R1 plus 1 over R2. So I'm going to do it the short way around, plus 1 over 1, the inverse of 1. Then you get 0.5 ohms. One way on how I can actually know this is that resistors in parallel, the total resistance must be smaller than the smallest resistor. The smallest resistor is 1. The total resistance must be smaller than 1. So that's how I know my answer is correct. So my total resistance will be 0.5. Remember the current, I have hypothetically used 1, and I'm going to put 1 there, meaning my voltmeter reading will be 0.5 volts. Now let's look at this one. I'm going to do exactly the same thing. R is equal to V over I. This is the famous formula. I'm going to say V because they are looking for the V over I. My resistance is 1. The current that will pass through there is also 1. 1 times 1 will give me 1 volts. So now, I just want to go back so that my numbering is correctly. So with the resistors in parallel, we had V2 and then V1. So let's go back here. So here we've got V2. We have V2 here. And then this one, we had V1 connected there. So let's see. V2 is 0.5. V1 is 1. What does this tell us? This tells me that V1 is twice that of V2 because 0.5 times 0.5 will then give you 1. So V1 is twice of this one. Let's go see if we have an option that says it's twice of that. And there we are. So this then will have to be number B. The voltmeter reading of this one is twice of that of V2. See, you cannot assume, you have to calculate. So let's look at 1.9. Now this is all about motors and generators. They talk about the maximum EMF, electromotive force, of an AC generator. Remember, that is alternating current. Now, one major thing that you must always remember when you're talking about motors and generators, first things first, you must always remember, am I talking about alternating current? Am I talking about direct current? Am I also talking about split rings, or am I talking about slip rings and the carbon brushes, right? And also think about the graph on how the current is actually going to move. Now, when you think about things like that, it makes it easier for any other question that actually follows. So let's look what they're actually asking. The maximum EMF of an alternating generator can be increased by doing what? So let's see. First things first, changing the polarity. Now, remember, when you change the polarity of your magnets, that's not really true because the polarity is actually determined by the current. So you cannot really increase the EMF by changing the polarity because that is determined by the current. Can we increase or maximize the EMF by actually using larger slip rings? Remember, when we talk about slip rings, they are the hollow rings that actually connect to the ends of the ammeter. They look like that. So as it actually rotates, it actually rotates through there. So that's not really true. We want to maximize the EMF, right? This just has a connection so that the current can actually flow. Then we can use larger brushes. Now, using larger brushes, this just means, remember, brushes is just a sliding contact used to transmit the electrical current. That is not really true. Those are the carbon brushes. If we increase the number of turns in the coil, then we can actually maximize the EMF. Remember, when you have an ammeter and then you only have one winding, it makes it a little wiggly, a little jerkingly, but the more windings that you use around it, it makes it more steady, and then we can actually induce the EMF in the generator. So when you increase the number of turns, that is then what we can do. I want to just elaborate further on these two. When you talk about slip rings and carbon brushes, most of the time you're actually moving from AC to DC. The components that make the generator or the motor, most of the time we talk about slip rings and carbon brushes. They don't really maximize the EMF, however, they change the flow of current and can actually change something from being a motor or a generator. Let's look at number 1.10. So in a house, appliances are usually connected in parallel to each other. Now, before I continue with this question, I want us to think about this actually logically. If you're in your house and you are sitting in the lounge and your father switches off the kitchen light, the lounge doesn't go off, right? The lounge light is still on. If your mother switches off the stove, nothing else goes on. So it means that it is independently by itself, meaning if one switch goes off and on, it does not really affect anything else. Remember, parallel connections, they are current dividers, meaning if you have 4 resistors, the current will split here and here and here and here. Meaning if you close the one flow of current, these ones can then still operate. And that is why our houses are actually connected in parallel. So in a house, appliances are usually connected in parallel to each other and because. Now let's see what can we rule out and what can we keep. The resistance of each resistor will decrease. Each appliance can operate independently. This is very true. What we just said, if you switch the one on, it doesn't affect the other one. The current supply to each appliance is higher. How do I know this? R is equal to V over I, famous formula. What do we know? Resistors in parallel, the total resistance is smaller than the smallest resistor. This means that the resistance will decrease and the current will increase. Resistance is inversely proportional to the current. Let's go back to here. Each appliance will have maximum voltage. Again, we are using this formula right here. So the only one I can rule out is the first one. So I can say 2, 3, and then 4. 2, 3, and then 4, meaning that my number C can then be correct. We can talk about them being independently, how the current will be affected, and the appliance having maximum voltage.